Oh, in algebra and group.
Okay,
Yeah, group
so that's,
computation.
yeah, I think that seems like it's working. Yeah, hi. So this is the first of the specialized courses. I'm going to talk about protocol verification, trying to put a little bit more of the V on the SPLV, although the PL is great. But just to give a bit more more of a round thing. And I've subtitled this now, a brief introduction to model checking and temporal logic. And if that sounds basic or something like you already know, I'm sorry, this is going to be a basic course, but I see that as it's going to, I pretend this to be a small, like a soft, slow introduction to the topic. And in that sense, also please, if something's unclear, stop me. I want this to have a very slow pace so that we can all understand. If you're all bored, then also just tell me to speed it up. That's also fine. But the goal is to be slow. So let's see if this works. Yeah. So what do I mean by protocol verification? Why do we care about this? I have the now kind of this is going in my face. Sorry, I'm gonna stay on this side of the screen. So the idea of like protocol verification, the idea is that we want to verify properties about something, and that something is what we call protocols. Never mind that picture. It's most times you write protocols, they look like some sort of weird diagrams. We're going to draw a lot of those weird diagrams. And I'm going to interpret what protocol is very broadly, and what verification is a bit more narrowly. It's basically a very precise definition of what kind of verification we can do and what kind of things we can, what kind of properties we can verify about these protocols. So what are examples of protocols? Like I'm going to give you a formal definition of what the models, like the things that we're going to check, but this is an informal. The informal part is the important here too, because it's important to understand what kind of things we can reason about with these methods, and also what kind of things we cannot. But I'm going to talk about the things that we can reason about. And by protocols, I mean basically anything where there's a specified order in which things have to happen, a specified way in which multiple actors respond to each other or interact with each other. And we want to be able to model this and verify this, verify properties about this sequence of interactions, these rules that rule how to communicate or interact between the participants. So a big example of places where you have these type of protocols are distributed systems, which are systems where you have different nodes of computation separated like physically in different places, and you care a lot about how they communicate. You care a lot about the fact that they can fail, for example, or not respond, that it'll take some time until the message get there. And so there's a lot of distributed protocols that tell you, okay, how do we agree on something, for example, in a distributed fashion? And here, this is a picture of some imaginary parliament in Paxos, an island in Greece, because there's a famous protocol that is based on this imaginary tale in Paxos, where people try to agree on laws, but sometimes they're not there, etc. And you want to make sure that in the end, everybody still agrees on what the laws were that were registered, and there's a mathematical formulation of a way to agree on these laws. But there's a lot of distributed protocols that tell you how you can interact in these distributed systems. Sounds completely different, but it's actually very related. Also, in hardware, you get these kind of protocols. So, this is not a coincidence. Ohad just mentioned it in the brief sharing. I also have worked on hardware, and this is where I've applied these things. in hardware, you have a bunch of small components, and these small components also have to talk to each other. So maybe you have multiple CPUs, maybe you'll have a memory controller, so you have a lot of different devices, and they have to talk to each other in certain predefined way. And we want to make sure that things don't break. Like if you have a bug in hardware, that's very hard to get rid of, that's very hard to correct. So we want to have ways of verifying that these interactions that we're going to define between the different components actually make sense in some way that we care about. There's cryptographic protocols like TLS or different ways of discussing making sure that you can securely send information from different ways, or that you can securely exchange information, etc. These are a bit harder. These are also protocols. Just the properties that we care about don't always cover these kind of things. So expect more useful things for these two kind of things, although you can reason about certain properties of cryptography, but there you have to reason about a bunch of other things that fall outside the scope of this. So I said, it's important to understand where this is useful. It's important to understand where this is not as useful as well. So that's the protocol part. What's the verification part? What's the kind of properties that we want to be able to talk about of these systems of interaction? One of the main properties, or a simple one that's also intuitive to understand, is fairness, right? We have a bunch of different systems that are taking turns on doing something. We want to, for example, describe a protocol that ensures that everybody gets their turn, that everybody gets their share of the pie in some way. And there's very concrete ways, and we'll see on examples concretely what that means. But basically, that a protocol doesn't necessarily favor one, or even could favor one, even if it's not, like, it might non-deterministically always be the case that something happens. In that case, we also that would not necessarily be fair. Like if it's possible to be unfair, we want to be able to reason about that. We want to be able to reason about freedom of deadlocks. This is maybe more specific, but also very central to this kind of reasoning. When you specify the way in which different things interact and the different actors interact, maybe one actor is going to wait for a message from someone else, and so this is a small deadlock for people, right? Like, oh, can we see the screen? Maybe this one has sent some messages here and is waiting to get a response from its predecessor, and this one has sent some messages here and it's waiting for a response from this guy, and so forth. And if we go in a circle, everybody's waiting for a response from someone else, but have not and cannot send something new because the thing is full. These kind of things is called a deadlock, because then the system cannot continue progressing. It cannot continue working. And if you have that in a computer, your computer will just freeze, right? So for example, if some sort of hardware protocol deadlocks, you cannot continue to read from memory, your computer will just freeze. We don't want that. And there's also kind of safety properties, right? If I have and we'll see this as an example. For example, traffic lights in a street, they define a protocol of how people can walk and how cars can walk on the street. We want to be able to make sure that this protocol is safe. Like, there's not going to be people and cars walking at the same street, like crossing the street at the same time, or else there might be an accident, for example. This kind of properties is what we mean by safety. And I'm being intentionally vague right now. We're going to be more precise later, but this is kind of the kind of properties that we're looking into, and not much more than this. A little bit more, but not much. So what is this course about, like in essence? Like what's the whole thing? So this was vague. Now we're going to be more concrete, and we're going to see the concrete flow of things that I'm going to talk to you about. I'm going to talk about one decision procedure or one decision problem, not even necessarily talk about the procedure. And the idea is we have protocols, like I said before, and we want to describe them in some language, in some formal system. And this formal system is going to give us these mathematical structures which we're going to look into, labeled transition systems. So we have, on the one hand, labeled transition systems describing models. And on the other hand, it's properties that we want to verify. So things like this, my traffic light protocol is safe, or my communication protocol is fair. These are properties of the system that I want to check. Like, does my protocol does my protocol enforce these, or do these hold for my protocol? And we want to write them in a specific type of logic. And in this course, this logic is going to be LTL, linear temporal logic. There's other logics that you can use, but again, I'm trying to be slow and basic for this course, and this is a very good logic. You can express a lot of interesting properties with it. So that's the one we're going to use. Also, we know good decision procedures for precisely this problem, right? Given such a labeled transition system and a statement expressed in this logic, does the statement hold for the system, or does it not hold? And if it doesn't hold, I can also build a counterexample or why it doesn't hold. And these counterexamples are extremely useful also. If you're trying to reason about a system, you want to see, well, I want to see if my traffic light is safe. If the tool just tells me, no, it's not safe, I haven't worked that much, gained that much from it. But if I get a counterexample, I can see, oh, this is how it doesn't work. This is how I can fix it. So this course will cover this left side of it. So we're going to talk about how do we describe protocols, what is the mathematical structure that we want to build to reason about them, and how do we describe properties in linear temporal logic. We're not going to talk about the decision procedure itself. How do we decide these kind of things? Maybe at the end we can briefly touch upon it, but it's by far not the focus of this course. So what will you hopefully know by the end of this? Maybe you already know it, but by the end of it, you will know what the formalism is of a labeled transitional system. You'll know what modeling languages are. How do we define this labeled transition system in some convenient language to define them? And we're going to specifically use Promela, or Promela, I don't know how you stress that, which is a language that's well established for this. It's not got all the newest bells and whistles, but it's venerable and useful. And we're gonna know linear temporal logic. And you'll have seen a bunch of examples, and I also want to stress this. The idea is that you know, okay, this is useful for these kind of systems. How can I describe them? How can I prove properties? So what I don't necessarily think you'll know by the end of this, because at least I won't teach it to you, is are other logics that you can use to express properties about these systems, other temporal logics like CTL star, for example, or like different types of computation tree logics, or the mu calculus, which is a more general way of that encompasses these things. And we won't really know the decision procedures for these problem, as I was saying. Okay, so that's the stage. That's what we want to talk about today. So we're going to start by modeling the protocol. So how do we define these models? And I'm going to start with the first thing I promised you'd know, so we can get that one out of the way: labeled transition systems. So a labeled transition system, you can see this is more on the theoretical computer science than the mathematics side, because we have these huge tuples of things. So we're going to, these labeled transition systems are these huge tuples of things. Let's start with that, and I'm going to tell you what all these things are and how we construct them. So the main thing is, like, these systems have states. So we have a set S, and we interpret whatever that set has as states. But formally, we just want this to be a set. And we have another set, S0, which is a subset of states. And we interpret these to be the initial states, right? So we're describing our system by states and transitions between them. So we want to have somewhere to start on the transitions. And we want to talk about actions in the systems. These are the transitions, which is also going to be just a set for now. So there's the set S and the set act of actions. And how do these transitions change the state of the system? This is this relation here, the transition relation, which I'm just using the right arrow for. It's a relation on S with itself, but it's indexed by the actions. So you can think of it as more precisely as a ternary relation on actions and pairs of states. And it's just a relation also for now. But this is what we model to be the transition relation. Then we have another set, which we call AP, which is a set of what we call atomic propositions. So these are the things, these are the labels that we care about. These are the properties that we care about for the system. But these are just atomic properties that describe the state. And finally, we have to relate these labels with the states that we have. So there's a function L, read for labeling, that takes in a state and goes to the power set of atomic propositions. And this is a function. When we call it the labeling function, because it's basically saying these are the labels of this state, right? So these are the propositions that hold that state S is L of S. So that's the definition of label transition systems, and that's what we're going to work with. There are different variations of this that you might see in different places. In particular, we're choosing here to put the labels on the states. You can put the labels on the transitions, etc. But this is one way of defining them, and you can translate it into a different formalism, if you so will. So I used this example at the beginning, the traffic lights, the protocol that describes how a traffic light works and when people can walk and when people can, when cars can drive, etc. This is a protocol, and we can describe this using a label transition system. So for now, it's just one traffic light, and it's a very simple diagram if you draw it on a board like this. Usually we use these arrows coming from nowhere to say this is an initial state, and that's just a convention. And then, so let's say that the traffic light starts red, then it turns green, then it turns yellow, and then it goes back to red. So that's kind of like the kind of diagrams we want to talk about to reason about these things. And then I can tell you how this corresponds to the formal definition we had before. We can just have the colors red, green, and yellow be our set. And this arrow here that says it starts with red just means, so here I'm missing the singleton set. So this is a singleton set, red. I don't care about the actions here. They don't have names, so I just use star, like a singleton set again. The actions are just, there's just one action, transition. And then the transition relation, this is the interesting thing, right? Whatever the transition, like the star transition just tells me red goes to green, green goes to yellow, yellow goes to red, which is this graph that we have here. And in this very simple example, we also don't have any atomic propositions. So that's just basically how to show how these informal pictures that we like to draw might correspond to the bunch of data in this construction. And these formal pictures, these pictures will also become formal in a bit. this traffic light is very boring when there's just one traffic light. It's not a protocol between any two things. So let's look at two different traffic lights. We have one for cars and one for pedestrians, which I'm calling walk, just so that it fits in the little box. And so if you see here, the car traffic light might turn red. It starts red. It might turn green. It goes yellow again and then red. So this is the traffic light that we had before. But now there's also pedestrian traffic light that doesn't have yellow in my model, just like here in the UK. And that one just goes from the walk from red to green and back. But now we have more actions. So we have this empty word here where I didn't label things. But then there's button pressed and button not pressed. These are two different actions that we might use to label things, these different actions, because we want to differentiate what happens when both are red. Like, did someone press the walk button or not? And now my atomic propositions, which are not here, but you can like see how it works, is, well, pedestrians can go when the pedestrian traffic light is green, and cars can go when the car traffic light is green or yellow. So this is what the labeling function also does, right? So for example, if the car traffic light is red and the walking traffic light is green, then pedestrians can go, and that's the single atomic proposition, right? Remember, this is the power set of atomic propositions. So this is just telling me what propositions hold in each of these individual states. I kind of need a way to interpret what that means. So this example, we have two different entities in some sense in the traffic lights, but we have just one label transition system. That's perfectly fine, and that's what we can use to reason about it. But usually when we're building these things, we want to describe what does the one traffic light do? What does the other traffic light do? How do we combine these? And so we might want to have ways of combining label transition systems to build newer ones, describing more complex systems. I'm going to show you a few ways of doing that. The first one is called an interleaving. And again, let's walk through this big definition. So, sorry, I pressed the wrong button here. So let's say we have two transition systems, TS1 and TS2, and we just index all the individual sets of them. Then we can define a new transition system, TS1, and this triple parallel line, we will just pronounce it interleaving, triple TS1 interleaved with TS2. And we define it just by building the big new transition system. So the idea of this is we want to, it's some sort of product. I haven't proved this, but I would assume that's the categorical products here in some sense as well. But it's some sort of product of the two transition systems. And you have the Cartesian product of the states. So one system can be in some state of S1 and another in the state of S2. And the actions as well, we just take the Cartesian product of the actions, the same for the initial states. And then for the transition relation, I'm going to explain it in a second, we take a new transition relation combining the two. But for the atomic propositions, we do something different. We take the union of the atomic propositions. Why? Because we don't want to be able to talk about the systems individually. We want to be able to talk about the full system, and we want to know which atomic propositions hold in this new combined state. And we also build some sort of product of the labeling functions in this way. So how do we define this L1 times L2 function, right? Remember, this is the labeling function. So it has to go from S1 times S2 to the power set of the new atomic propositions, which is the union of the atomic propositions. And we do this the obvious way. So we say, if we take this new product function of a tuple S1 and S2, that's just taking the atomic propositions of S1 and also the atomic propositions of S2. So we take the union of the two. And the this transition relation we define basically by these two rules. And the idea again here is this is supposed to be the interleaving of the two things. So one system is going to do a transition or the other one. So if S1 would transition with action alpha to S1 prime, then the combined system transitions also just on the left component with alpha. And here on this case, if S2 would transition with alpha to S2 prime, then just the second component transitions to S2 prime.
So the act is the union.
Sorry?
The act is the union, maybe?
Oh, I see. Because I'm
because it's the alpha is the same.
right. Yeah, because the actions because well, I mean this is the same alpha can be in both. Yeah. So the actions
The action could be on both LTSs. Wait, no. I have also another question. So usually, so I've been used to using the word label transition system just for S act and the arrow, and the labels would be the actions. So
Okay.
you have another term maybe for this one, so that I can Google it. Like the labels here goes to atomic propositions, and then I know nothing about this. So maybe you have another term that I could.
I don't know a different term of label transition systems to that. I've heard script key structures for the one that you're describing, but I think the terminology differs here. Thanks. There's a question there in the back.
Yeah, I'm also confused about like the actions 1 times the actions 2, because this means that your action is always a pair of 2 actions.
Yeah,
for
yeah,
the
yeah.
Individual
No, I
systems.
think it should be the union.
Okay.
Yeah, sorry.
Yes.
Okay, so we call this the interleaving of the two systems because basically either one system takes a step or the other one takes a step, but not at the same time. So in some sense, this means that these two transition systems are working independently of each other. They don't really interact. They just, one does its thing, the other one does its thing. And if an action is in both, then you can non-deterministically choose which one of the two does. So we can look back at this example of this traffic light. This is the traffic light with 3 colors, red, green, and yellow, and just take the interleaving of the two, and that gives us this bigger transition system. We might want to look at it a little bit in detail to understand this construction. So the product of the two states means we have one of the two systems is in one state, the other is in the other state. And because these two start on red, right? So we said the product of the initial state of the product is the product of the initial states, right? If we had more, you could have the full product of things, but here it's the 2 R's.
Please tell me there's a latex package for interleaving diagrams so that the lower thing is just TIKZ interleave of the 2 upper things.
No, I did this by hand. Sorry.
Nice.
I don't know that there is a package for that. It's fun to draw this by hand. It's somewhat meditative. Yeah, by computer hand. Yeah. So yeah, as I was saying, the initial state of the composition is the composition of the initial states, or the Cartesian product in this case. So it starts with both at R1, and then you can see here kind of reflected the transition system of the first one. So red, green, yellow on the first component. Here, red, green, yellow on the second component, on the first, and here again the same. So in these 3 circles, just the first component is changing. So these are kind of the actions of well, in this case, we just have a single action. Doesn't really matter, right? But it's kind of morally, the first thing is taking an action. So it'd be the first rule, the left rule, and then the second rules are these bigger arrows here that take the second system to it, and you can also see kind of the big system mirrored in these like subcomponents in some sense. So that's kind of what the interleaving does. It builds some sort of product of the transition systems. But the interleaving is not so interesting because the two things are not interacting. That we could just look at them independently. Why do we care about their composition? We usually care about their composition when there's some interaction between the subcomponents. And so I'm going to define a new type of composition, which we call a handshake composition. And this kind of lets you model this kind of interaction where things actually do interact with each other. So again, we have two transition systems, TS1 and TS2. And in this case, we have some sort of actions, H, which are in the intersection of the actions of the first one and the actions of the second one. And now we define this transition system here as the parallel composition with handshake H. Here's the same type of this. So this type checks, this has to be the union. So how do we define the handshake? It's again the product of the states of the two parts, and again the product of the initial state. We do the same thing with the atomic propositions and labels, but now we define the transition relation in a different way using H. So there's kind of two cases here. One is when the action is not in this intersection, in this handshake intersection. So let's look at those first. So if S1 transitions with alpha, so this is the transition function of 1 to S1 prime, then it does so on that component. And the same for S2. So these two are the two we knew from the previous construction from the interleaving. So if they're not handshaking, they're just interleaving in the general way, they're not interacting. But if the action is in this handshake set, then we get a new composition, right? Like we're saying S1 goes to S1 prime, and this should be 2. I'm sorry, S2 goes to S2 prime with the same alpha, but this also the second composition. Then we can go at the same time using alpha from S1 to S1 prime and S2 to S2 prime.
I have two questions.
Yes.
The second of which is designed to be annoying.
Okay. Good that it's the second.
The first question is, thank you, this is completely clear, very, very clear. But sometimes, let's imagine two communicating processes and one of them sends a message out.
Yeah.
And the other sends it in.
Yeah.
So out is not equal to in, but clearly
Right.
it's in the spirit of a handshake.
Yes.
So I'd be interested in your comment on that. And the second question is, what about an alpha which might participate in a handshake or might not? So the example that springs to mind is I might send a message, I might receive a message, but I might receive a message from my wife, or I might receive a message from some other part of the environment. So how would that fit into
Which one would you actually handshake with?
my wife, I should
Okay.
say. Yeah, thank you.
Sure. Just to be clear. Okay, so I hope that I think I have the same answer for both, and I hope that satisfies you. But if not, we can talk about more offline. But the spirit of this is the mathematical model that you use to describe the systems that you care about, but not necessarily the mathematical model you use to specify. So I think of this as some sort of intermediate representation, some sort of mathematical intermediate representation, just in the same way that you might write Haskell and not core. You don't want to write, I don't want to write things in lambda calculus. I want to use another language to describe them. And then I elaborate into the core mathematical structure the same way you would do this here. So when you have, and we'll see examples of that, but when you have a channel sending a message and another one receiving a message, that's a separate action that says channel 1 sent a message to channel 2, basically. That like you would have the concrete channels in that action alpha. So you'd have a different action for every pair of interacting channels, and that's fine. But that's just gives you the so that you have like equality of the actions on this intermediate representation that's representing it. And in the same way, if you want to interact with some and not with others, you just have to bake that into the set of actions alpha. So you'd have different actions for you're getting a message from your wife than you're getting a message from the environment.
That's clear. So just to clarify, I think what you just told me to the answer to the first question is there's an independent in and out action, and then there'd be some kind of alpha, which is the message. The out action and the in action actually getting transmitted, and that would be the handshake.
So that would be one way of modeling it. You can also model it as a handshake transaction between the one. So it depends on whether you're kind of modeling the messages to be sent synchronously or asynchronously. But what I'm saying, that the higher level point that I'm saying, and I will come back to that as well, is you want to have some sort of modeling language that you use to construct these systems. And in that modeling language, you will have also some sort of actions at a different level of abstraction that you.
Is that level of abstraction higher or lower? That's the one bit I haven't got.
So you'd have an action send message, and that send message from A to B, an action receive message from A to B, and then when building the transition system from that program graph, or however you want to define them, then you'd have a construction that builds a bunch of new actions from the two kind of abstract actions of sending and receiving a message. Or process 1 receives a message from process 2, process 2 receives a message from process 1, and so forth.
Thank you.
Okay. So basically this new construction we call the parallel composition with handshake H, and H, I said it can be some sort of subset of the intersection of these two action sets, but when it's precisely the intersection, we can just omit it. We just write parallel. I didn't put it anywhere. Like we just omit the H here as well. So how does this handshake look like for these two traffic lights that we had before? So now we have this button being pressed and not pressed, and button being pressed and not pressed. And when we combine them, so in this case, I've cheated a little bit because I put basically the pedestrian traffic light stays red when the button is not pressed, but it
Those actions are flipped, right?
they are flipped. I wanted to cheat and I missed. I miscopy pasted. So this would be button pressed and button not pressed. Kind of saying basically, one does the opposite of the other one when the button is pressed, right? And so, these two should be the other way around. And then you can combine them, and then you can see how this one, we get basically this is the one that we had before, and we get it by combining these two with handshaking on these two actions, that the button is pressed and the button is not pressed. So again, we can also, as we've heard a preview before, we also want to be able to like talk about message passing. And so this is a different example. So maybe you want to have two processes working on different threads in a computer system, and they want to talk to each other in a shared memory system, and to be more precise. So I can use message passing between the two to be concurrent. And so let's look, this is two copies of the same thing. And so here we start with, we have a flag variable and a variable that says I'm in the critical section of whatever I'm going to do. This could also be a message that I'm sending, but in this case, I'm just using the same pattern. And so here we have two actions which I've labeled with these this type of brackets to be generic. So I'm saying self and other because we're going to build different actions from them. So we're going to interpret them differently when combining them, like in this higher level. And so if you have this, if we have this flag and the critical section are at the beginning is 0. So if it's my turn, I set my flag to 1 and saying this is my turn, and then I can go into the critical section. After the critical section, I should have. That's the problem of doing this by hand. This critical here should be 1, and so after this critical 1, you can go back to the beginning and set both to 0. So this should be a 1. These two. So when we combine them, right? So this self and other become 1 and 2, and they're interpreted differently depending on who's being composed with who, right? So if this is 1, then self is 1, other is 2. But in this case, self is 2, other is 1. So this is kind of the translation, like you describe this in a higher level setting, or you would define them as two different ones, where 1, 2, 2, 1, depending on how you want to see this. But that's precisely the thing that you're doing, like you're describing this more abstractly and then instantiating it with the 2. There's a question from Jesse.
So wait, why do we have loops on the bottom for?
Oh, because this can also always, we can always choose that it's choose to have the other one do nothing. No, wait, but that's okay. I see what you're saying. Because then this would be also in the handshake one. So we shouldn't have these loops.
Okay, thanks.
Sorry, that's good observation. Thanks. We wouldn't have these loops at all. Actually, also this one not, because in this case, this loop actually becomes this arrow. So we wouldn't have any of the loops. Yeah, thanks. Yes.
So are 1 and 2 just annotations here, or do they actually participate in the protocol?
So 1 and 2 are the actions, the message actions that we're giving them, and they are so the handshake set in this case would be the set containing 1 and 2, basically, because so maybe I should have called this, instead of putting these brackets here, just said 1, 2, 2, 1, and then that would be more direct. But I wanted to make also the point that you kind of want to instantiate this with the concrete actions depending on how you're instantiating them. And we're gonna see a bit more precisely, not super precisely, but a bit more precisely how you get from this to instantiating the 1 and 2. But it's just to convey that idea. I don't know if that makes sense.
Can you go back to the parallel definition?
This one?
Yes.
Yeah.
I'm a bit unclear, like, doesn't this allow you have the top 2 transition functions where you transition in either system 1 or system 2?
These two?
Yes.
Yeah.
Doesn't this let you just transition one of them independently while the other one is in the critical section?
So absolutely it would, but it depends. There has to be this arrow that takes this state to that state, right? And so while this one is in the critical section here, the other one is in the state where both are 0, right? So flag 2 is 0, critical 2 is 0. So in that state, the only transition is the self loop transition, or like these two are the only 2 transitions that you have, right? And they are the 2 handshake transitions. So the state that you're in here, that system 2 is in this, right? Like if I was to split this one apart into the 2 individual states, system 2 would be here. So there's no way that it can go into that without the action self. So without the action 2, but that's not the action that we have at this point. Does that answer the question? Okay, thanks. There's another question there in the back.
I think it's related to that question, in that I don't really see, like, shouldn't, like, for example, the flag, like, variable or whatever, be shared between, like, both states? Because I don't understand why, like, on the combined one, for example, if it's like on the, like, flag 1 is 1, and it has flag 2 and critical 2 is equal to 0, why this cannot just start putting its own flag to 1, so that, like, so that flag 2 is 1.
Right. So that is a good question, because basically, because we're modeling this too abstractly, and I'm assuming that there's some mechanism to enforce this 1 or 2. And actually, that was kind of one of the things that we're going to hear here is, like, we're kind of assuming that I can read the flag, see if the other flag is set, and then decide to go into 1 or 2 atomically. And I don't know if that's I do know if that's a reasonable assumption, but I want to pose the question here: is that a reasonable assumption? And I think it depends. It depends on the hardware system. There are some systems where you can do this, but not necessarily always. So thank you. That I was kind of going for that. I was trying to make that, build that issue in there. Okay. So another example of a different type of protocol is the MSI cache coherency protocol. I realized that this thing never went away, but it doesn't. This says coherency protocol here, and this is just to go into a bit more complicated examples here, just to give you a small notion of this. This is the picture that you'll see in a book about hardware when they're describing the MSI protocol. And the MSI protocol is, so just in case, just for context, so that everyone, so we're on the same page. When you have a system with multiple processors that share memory, you usually have these things called caches with the processors, which are much faster to be addressed, and they kind of copy the information from main memory into the cache. But what you want to have on those is to make sure that the values in that copy of the memory are consistent across all the copies, right? Between the caches and the memory itself. And so this is the protocol that people use, or this is a classical protocol people use to describe these kind of systems here. So this is actually copied from a book on hardware. So you have these cores and you have these cache controllers, which is the piece of hardware, the logic that makes sure that the cache does the right thing. And here they can access here their private caches, and then they communicate with memory. And there's also a controller in the memory. Like, basically, these pieces of hardware have to implement some logic to make sure that the data makes sense. And this is the protocol that you use here. And you can see it's very similar to what you have. So you have 3 states, MSI in this case, which stand for modified, shared, and invalid. And you have different actions depending on the interactions, the things that you get from the memory controller or from the core, you do different actions. And we're not going to dive deep into how this preserves the coherency of the cache, but this is kind of the picture of the things that the picture that people draw to reason about them. It's also a representation of the structure that we can use to reason about them. So how do these pictures come about, right? Like, these transition systems are not graphs per se, but these graph visualizations that we've been using are very useful. So how do we build these graphs? They have a very concrete definition. So we want to be able to reason about the steps that we take in the graph. So we have this definition of predecessors and successors in a transition system. If we have a state S and an action alpha, we can say the post, so anything that's coming after, like the successors of state S with action alpha, are basically all the states that you get to with alpha. And if I take the union of all such alpha, those are the successors of state S. So we care about the successors of state S, and we can define a similar thing called pre for the predecessors if we just flip these two here. And in this sense, we can also define some sort of graph, the state graph of a transition system. So if we have a transition system like this, we can build a graph G of TS, the state graph of TS, by just taking the states as the nodes of the graph. So this is a directed graph, right? The nodes of the graph are the states of the transition system. That's why it's called the state graph. And we construct the edges using this successor condition. So we're gonna say the pairs, this should have parentheses here, the pairs of every pairs of S comma S prime in the product of states is an edge in this graph if S is some state. So for any state, we just put edges on the successors on this post set of S. Right, basically, in other words, if I have some transition alpha that takes me from S to S prime, I just have an edge and I forget about the transition. I forget about the label of the action, to be more precise. So that's how these graphs come about. And these graphs are useful because you can use graph theory to reason about things, like reachability, for example. Reachability is quite useful. So following this analogy of graphs, we can also think about paths through the graphs, which basically represent what's happening in the system. So we can define path fragments this way. So if I have a sequence pi 0, and I don't quite like this myself, but in this case, it makes sense to start counting with 0. So if I have a sequence of states, pi 0, pi 1, pi 2, and so forth, I call this a path fragment basically if the next element in the sequence, so pi I plus 1, is actually a successor of pi I for all the i's. Basically, I go one by one. Each time there's a transition that takes me from one state to the other. So if this is a finite sequence, then also so if this is not indexed by n, but it's a finite sequence, then I also kind of a finite path fragment, and we'll use these these angled brackets here to talk about the ith element of the sequence, and also like use sort of this notation to talk about some subsequence of it. So in a sense, these path fragments are just sequences of transitions that can happen in the actual graph.
To call this a path fragment,
To call this a path fragment
Yes,
suggests that there is a thing called a path of
Correct.
which it.
That's the
in
next
slide. Yeah.
Yes.
Okay, thank you.
So this is called a path fragment because a path has to have some conditions. One of them is being initial. So if it starts in an initial state, it's an initial path, right? We sometimes want to talk about starting from some state in the middle, but often we want to talk about starting from the initial state. That's why it's called initial. And we can call it maximal if there's no other path fragment that it's a prefix of, a proper prefix of. So if I cannot extend a path in any way, then it's a maximal path fragment, a path fragment. Sorry. So correctly, a path is a path fragment that's initial and maximal. Basically, it's a sequence through this graph that starts at the beginning, and it doesn't cut short at any point, right? There's always an extension. So that's a full path. Yes?
let's imagine going out in a circle.
Yes.
So
I'm doing the housework, I do the dishwasher, then I do the laundry, then I do the dishwasher, then I do the laundry. So my initial state might be the dishwasher.
Yeah.
I do that, then I do the laundry. But then I go back. And I do the dishwasher and the laundry again. Is that a path? Because I've gone in a loop back to the initial state.
If there's a transition that takes you Back, yes.
So it is possible for something to be a path and yet to be a proper subpath of another legal path in the presence of loops.
No, then it wouldn't be maximal. Yeah, so I guess that would be an initial path fragment. I don't have your transition system in my head. So
Okay.
if there's something to do at the final state of a path, then it's a path fragment.
Ace, thank you.
In part of our definition, we didn't require that there always be a step to take, right? Like we can hard terminate.
Yes.
Okay.
Well, I'm gonna talk about that as well. Yeah.
Yeah, I mean, it was basically the same thing. I was going to say that it's like a maximal path doesn't mean it just terminates into like nothing, like,
It either terminates into nothing
or it goes back to the initial.
or it loops on forever in some way.
Okay.
Okay. So some examples of paths. There's some typical this traffic light example, and this is how it feels when walking in the street here. In this traffic light example, cars get green, yellow, red, green, yellow, red, and the walking one is always red. That would be a valid path fragment here, right? Or that would be a valid path if it loops on forever. What would not be a valid path fragment is if the cars are yellow and then go to red, but at the same time the pedestrian one goes to green, because we're modeling things atomically, and so which in this case means from this state car red green, car red walk green. From here there is nothing going. Wait, no. Sorry, car yellow walk red. So from here to here, yeah, exactly. There's no arrow here, so I cannot skip. I cannot take multiple steps. Right. So if I have a finite path fragment, I can always keep on going and extend it to an infinite one. But like some of you asked, you gotta have a stop here, and usually we use these two circles to say that's a final state. There's no transitions going out of here, right? Like I didn't in any way ask that there's any transitions out of it. So we can either reason about these kind of finitely hard terminating things, or we can just construct a different, right? I don't have, sorry, the post of this Sn is 0, or I can actually build a construction that lets me also always loop forever, so that all my paths are infinite. So I can always add an additional new state that's like a capture state and just loops on forever here, right? So if I have this kind of thing where I cannot get out, I can always loop forever. And for the rest of this course, we're going to assume that we don't have these kind of states, except for when we're going to talk about deadlocks. But yeah, that's where we're going to leave it for today. And yeah, tomorrow we're going to talk about how we built these more. Thank you.
Right, so folks, we want to stay for Bob's implicit complexity. It's in this auditorium, otherwise Sam's effects and handlers are on your right. You can exit the room on the right-hand side.